Okay, thanks for the introduction. First, I would like to thank the organizers of this meeting to give me the chance to show my work. And I'll be talking about the theory of spike timing based neural classifiers. And I did this work together with my advisors, Professor Chaim Sopolinsky and Professor Rubin from Paris. He said, what's pointer? My pointer. Okay, with Rubin in Paris, and of course in collaboration with Robert. So what I'll talk about here today, this is the outline of the talk. I will start by presenting the Perceptron, which probably most of you already know, but it will be a good reference and a point of comparison to keep in mind when we will speak about the theory of the Perceptron, which is an integrated fire neuron that learns to classify input patterns that have input in the timing of the spikes and not just the rates. And after that, I will discuss what I hope is interesting and maybe a bit surprising result about the relationship between the synaptic weights of the neuron and the input-output function of this neuron. And in the end, I hope I have time, I'll show you some new results about trying to extend the capabilities of the Perceptron model to learn precise timing, or to have precise timing of the output of the Perceptron. So the first question to ask maybe is why I will speak about spike timing based decision, and the quick answer is that at least in the brain we find some systems that use spike timing information, like several sensory systems. So I'll just give you one example from the lab of Markus Meister and Tim Golish. So these are recordings from the retina of the salamander, and you can see the response of the neuron as a function of time, and every line in this graph is a response to a different stimuli, and the stimuli is just gratings that are at different positions. So you have a grating, and you move it from position to position, and what we see is that the neuron codes the position of the grating according to the onset of the timing of the onset of the firing of the neuron, and not in the rate. So in a sense, it's the rate of it's the spike timing code and not a rate code. And the Perceptron gives us a way to learn these rates, and I will show. And what I try to do is try to analyze how he does it, and what are the capabilities, and what can you learn, and how much. Okay, so we start with the Perceptron. Just a quick reminder: the Perceptron model. What is the Perceptron model? Very simple architecture: a singular neural network. We have input layer with n input neurons, and R as these are the activities or firing rates of these input neurons, and one output neurons. And this output neuron has a set of synaptic weights, and the potential of this neuron is just a weighted linear sum of the activities of the input layer. And the output of the neuron, we take a binary decision output. So the output of the neuron is +1 if the memory potential process some level of some threshold level, and -1 if the memory potential of the neuron stays below the threshold. There's a nice graphical interpretation of what the Perceptron does. So this is an example in 2 dimension, and I have 2 inputs and 2 weights. I can plot both the weight space and the input space on the same plane because they both have 2 dimensions. So this is some input point that I want to classify, and this is my weight vector. And what this weight vector does is divide the plane into 2 parts. Everything that falls on the right of this plane is classified as +1, the output is +1, and everything that falls on the left of this plane, the output is -1. And if we have some more points, this is the classifications. Okay, so a lot is known about the Perceptron, mainly examine the properties of this model, we have to define some specific task. And the task we want to consider is the classification of random patterns. So we have a set of p random patterns. Here I present to you an example of them. So here the input rates are binary. So what we see here, each line represents the input from each of the neurons. And if we have a blue line, it means that the input of this, the input of the specific neuron is +1. And if we don't, then it's 0. And we divide these two classes of patterns into two groups. For the first group, we call it class patterns, and the output of the perceptron should be +1 when presented with these patterns. And for the second group, the output of the perceptron should be -1 when presented with a pattern from this group. And our task is actually to find a weight vector of the perceptron that classifies the patterns according to the desired labels. And we call this weight vector a solution. And the set of all weight vectors which classify a given set of patterns according to the desired label, we call a solution space. So usually we have many types of solutions, and they form some volume inside the entire n-dimensional space of the weights. So I can schematically draw this in simple boxes. So now each box is the n-dimensional space of the weights. Each point in the box is one weight vector. And the blue region inside each box is the solution space. So every point inside the blue region is a solution to the specific classification task. And what I show you here, so first of all, it's very easy to prove that this volume is one single convex volume inside the weight space. And as you increase the number of patterns you need to classify, this increase the load on the perceptron, this volume shrinks. And as you add more and more patterns, eventually you come to a point where this volume is just one point, and after that it disappears. And we call this point the capacity. And this capacity defines us actually the maximum Pmax, which is the maximal number of patterns we can classify. And what's important to understand is the connection between the capacity and the point where the volume of solution disappears. That they both define the same spot. And a very well-known result for when n is much larger than 1 for large n is that Pmax is proportional to the number of synapses and with a proportion factor of 2. So we say the capacity of the perceptron is 2. Okay, so these are the main points I want you to remember about the perceptron model. And before we go in, now I'll describe the temperature model and the theoretical results we found on this model. So the architecture of the temperature model is very similar to the perceptron. Again, one input layer, one weight vector, and one output. But now the inputs are dependent on time. So here I present to you an example of an input pattern. The input pattern starts from time 0 and goes to time t. This is the time axis. And each line represents the activity of each of the input neurons. And when there's a blue line, then it means that the input neuron spike, there's an input spike coming from this neuron at this time. Okay, so these are the kind of patterns the neuron sees. And what it does, it's such a simple integrated fire neuron. The voltage, the memory potential of the neuron is some resting potential plus some weighted linear sum of these kernels, which represent the effect of each input spike on the membrane potential. And of course, we have the membrane, the neuron has some threshold voltage. Whenever the voltage crosses the threshold, we have a spike and a reset. So it's the fairly standard model. What do we take as the output of the neuron? We take a binary decision rule. So we say that the decision of the temperature is +1 if the neuron spiked at all at any time from time 0 to t, and -1 if it stays quiet. So here I give you an example of a plus pattern, okay, because here the voltage crosses the threshold. And this is an example of a minus pattern because you see that the voltage stays below threshold throughout the presentation time. the task that we want to examine is similar to the task we had for the perceptron. We want to classify again p random patterns. So what are random patterns now? We just pick random latency patterns where the input from each neuron is just a random Poisson with rate of 1 over t. So the average number of spikes coming from each neuron is 1, but it can be more or less, and the timing is just spread randomly.
So it's not the latency, I mean, there are more than one spike.
Yeah, so it's
might be more.
You can say it's a combination between a rate and a latency. So if you think about it, you can think about it. So what would the perceptron do if you take this input, just sum all the inputs and translate into a number, the spike count? So the perceptron, we know what it will do. The capacity will be 2. But we already know from Hyman and Robert's paper that the capacity here is bigger.
Either the input is silent or it has a rate of 1 over t.
No. The input always have a rate of 1 over t, but if there might be some realizations that there are no spike are coming until time t, and then after we draw these patterns, we keep them fixed.
Oh, I see.
Okay, so this is very important. Yes, very important. We generate these patterns from Poisson processes, but once generated, they are fixed. The timing are fixed, and every time the temperaton sees this pattern, it sees exactly these spike times. Thanks. Okay, so what Chaim and Robert did numerically is just to test whether or not whether the temperaton is doing good or bad, and this is the result. So what you see here on the left side is a graph of the learning time. Okay, so how many times we need to present all the patterns in order to find a solution. And we say that if we are close to capacity, it will be very large. After capacity, it will be infinity because we will not succeed in learning. And far away from capacity, it will be very low. And you see as you increase the loads, you add more and more patterns, this learning time increases, and it goes to infinity somewhere around 3, okay, which is more than 2. So the gray line here is the performance of the perceptron, just for comparison. Okay, so the perceptron goes to infinity around 2, and the temperaton does better around 3. Okay, so this is the first result. The second result, the second thing they found is that there is very big dependence of the temperaton performances on the time scale of the kernel. Okay, so what you see here is for a fixed load. Okay, the number of patterns is constant. We just change the temporal, the time constant of the kernel, and you see that there is some optimal time where the learning is fastest, meaning that we are farther away from capacity. And when we change this time, either make it longer or shorter, we get closer to capacity and eventually above capacity. So the questions we did, my theory, our theory that we have developed is going to answer these questions. So how does the capacity depends on n and the time constant of the kernel? And in addition, we would like to know, like we know for the perceptron, what is the solution space, how does it look like, and how does it evolve as we add more and more pattern, and how does this compares to the perceptron? So the main difference between the temperaton and the perceptron, and the main element that, or the additional element that we have in the temperaton, is that we have the temporal degree of freedom, that we have the freedom to choose when to spike at different times. And then the number of choices that we have, or how much freedom do we have to choose, is determined by the time constant of the kernel. Not the time constant itself, but its ratio to the overall presentation time of the pattern. So if the pattern is presented from time 0 to t, then we define some parameter k, which is t over tau. Okay, and I give you here 2 examples to show you that the behavior of the temperaton is very, very different in different regimes of k. So when k is small, we presented some random pattern, and you see that the voltage is very highly correlated in time. So you can say that the number of decisions, or the number of opportunities the Templeton has to spike in time t is very low. I don't know, maybe 1 or 2 or 3. However, when you increase k, so when k is much larger than 1, let's say 100, you see that the correlations in the voltage are much shorter, and we have the Templeton has an opportunity to fire at many time beams and can make many decisions. And the question we ask is, what range should we be interested? Because these are clearly qualitatively different. So the answer is that theoretically, the best the best regime where we can understand the behavior is this limit, where we have many opportunities to decide. But when the size of the system is much larger than the number of decisions we can make, and fortunately, maybe the biologically interesting range, if you think about a neuron with 1,000 or 10,000 inputs and some patterns, a presentation pattern that has that comes in for half a second and a time constant on a few milliseconds, we get k in the order of the hundreds. So this is exactly this kind of limit where n is much larger than k, and k is also much larger than 1. So how do we approach this to analyze this task? We use the same statistical mechanics that was used by Garner for the perceptron. We try to use it here, and what we want to calculate is this volume. To find out what is this volume of the solution as we increase the load on the temperature. So if we look at the expression of the volume, we call it the Gardner volume. You can see it's quite simple. So it's just an n-dimensional integral over the entire weight space. Okay, and here is just a product over indicator function over all the patterns that tells us whether or not these patterns are classified correctly or not. So what we have inside is just, here we have a maximum over the voltage generated by pattern mu minus the threshold, and if this is, and this times sigma, which is the required output of the perceptron. So if this is larger than 0, then the pattern is classified correctly, and we have, this is a step function, and we get here 1. And if this is negative, then we get here 0, and we don't count the point in weight space as part of the voltage. What is important to note here is that the decision is based on the maximum of the voltage. So if you think about it, for different sets of weight, the donation from the contribution to the integral from patterns from a specific patterns can come at different times in time. Okay, so the temperature can perform the same classification, but in many different ways. Every time he will, for every kind of solution, he will spike at different times for every pattern. So what we want to calculate, what we do to find out the typical behavior of this volume is to calculate the free energy, the average free energy. So this is just specifically for a given set of patterns and given set of labels. What we want to do is find the average over all the spike trains, all the input spike trains and labels, and find the capacity. For example, find the capacity by finding where this volume vanishes or this free energy goes to minus infinity. So this is what we did, and I'll show you the result. So first, the theoretical predictions says that the critical capacity in this, asymptotically in this limit, goes like log k over 2 log 2. The important thing about this is that it is monotonically increasing with k, and the dashed line is the theoretical line. You can see it's so here we have the x-axis is k, and this is the capacity. Here is 2, so 2 will be the capacity of the perceptron. So we see it's always above 2. and this is the theoretical line. And the most obvious thing when you look at the simulations, these are the simulations, is that the behavior is not monotonic. So, but this is fairly easy to understand because this result is only true in this limit. But as we increase k, eventually we come to a point where k and n are of the same order of magnitude, and we cannot expect this result to be true. And in addition, it's very easy to understand why the capacity drops, because when k is much larger than n, only the time differences between two incoming spikes is larger than the time constant of the kernel, so there's no integration of different spikes. So you only have a small bump in the voltage proportional to the weight of each input, and you cannot do much with that. And of course, and when k is infinity, we expect the capacity to be 0. What is important to know about the simulation result is that as we increase n, so this is n is 250 neurons, this is 500, and this is 1000. As we increase n, the onset of this effect gets farther away, as we expect, and also the effect is weaker. So we get closer to the theoretical predictions as we increase n. So this is why we believe this non-monotonic behavior is only due to finite n effects. So this is the capacity. What about the solution space? How does this compare to the tempotron, the perceptron? So what we do when the result of the calculation we did is that we can describe the solution space by two parameters: Q naught, one that we call Q naught, which all it represents is the total size, just the characteristic length of the entire solution space, and Q1, which represents the characteristic length of the size of volumes in the solution space that solves the classification problem in a similar manner. Okay, so that the temporal pattern of the output spike is the same. Okay, so yes.
What do you mean similar? What is the metric to measure to compare?
Oh, so I don't want to define exactly the measure, but what is important to understand is that they fire the output spikes for given patterns are similar. You can say they're the same, or the same. They are maybe tau apart, mostly tau apart. It's the most trivial definition. Okay. So what we can do is calculate these two parameters as a function of the load, and from the result we get from the result I can show you what we believe is the evolution of and geometry of the solution space as it evolves. So this is how it looks like. These are the equations that describe the two order parameters. And don't worry. Just to let you know
You have to worry.
Yeah, no. So I have worried about them for a long time, and it's okay. They are correct. But this is the story that this equation tells us. Okay, so here we see the picture that we saw before of the perceptron, and for comparison we see that the picture for the tempotron is very, very different. Okay, so at the beginning, so we have first of all, the main thing to note is the solution space is not convex. Okay, because we have many different ways of classifying the patterns with different weights, we don't get the convex shape of the solution. But in the beginning, we still have a big bulb, one big volume that all the solution lie inside this volume. Then, as we add more and more pattern and increase the load, at some point, there's a critical point where this structure breaks into many separate clusters. And as we add more and more patterns, these volumes divide and shrink. And at the end, at the capacity limit, we have many very small volumes spread around evenly throughout the entire weight space. Okay, and as opposed to the capacity, they are not points. They are finite. They have some finite size, and at the capacity, they all vanish immediately.
What are the dashed lines on your figure?
So the dashed lines are supposed to illustrate regions in weight space that classify the patterns in a similar manner. So this would be the Q1 parameter. So this the size here is Q1 represents the size here, and Q0 represents this size. So here and here, so here you see Q0 is that the size is large, it's the entire weight space almost, but the Q1 is the size is smaller.
So when it first shatters, it doesn't shatter first into two parts and then more. It always shatters straight away to multiple. Is that diagram correct?
That's a good question. The theory doesn't give us the tool to answer it precisely. Typically, in this system, on similar systems, we know that it shatters immediately. It shatters to many volumes. Okay, so it's a critical point. There's this critical load at which below it it's connected, and above it it's completely shattered. Yes.
If I understood correctly, the role of the parameter t in the one that is twofold. It is both the time window and 1 over the typical rate. But if you allow many the firing rates in different input channels to be different, like in my spectrum, then there won't be a characteristic time constant. Maybe how will it affect the results? Do you understand what I'm saying?
Well, if you have many different rates and very high rates, then speaking about then you go back basically to the perceptron.
Then you need kernels with the minimum time constant that will integrate everything. Like you just take 1 over the highest frequency.
No. Okay, I think the frequency of the input is 1 over t, the rate of the input.
Not all of the inputs are 1 over t. What happens if there are different input frequencies and different channels? Then.
Alright. So I mean, you get more input from certain neurons and less from others. But this is exactly what happens in the perceptron, right? So the motivation of taking the rates the same is to be able to say that what we are looking at is the spike timing and the information that is encoded in the timing of the spikes, and not the information that is encoded in the rates of the spikes. Okay. So just to summarize quickly what we saw, this is the perceptron. We have the capacity is 2, and the solution is convex. And for the temperature, we've shown that the capacity is proportional to the number of synapses, monotonically increases with k, and that the solution space is fragmented into small clusters. And what I want to discuss now is the significance of this last result. Okay, so this is the part about the relationship between synaptic weights and the neuron's input output function. So if we think about it, these two models, and we look about two weights that solve the same classification problem. In the perceptron, in order for two weights to solve the same problem, they must be inside the solution space, and they must be very close to each other and be very similar. In the temperaton, in contrast, even two solutions can be very far apart. They can be they are almost orthogonal to one another. Completely different set of weights, but still that can make exactly the same classification. On the other hand, in the temperaton, even if we take two close by weight vectors, but one is inside the solution space and the other one is outside the solution space, so even though they are almost identical, they make different classifications. And the question is, one natural question to discuss is, okay, maybe they are close by, maybe they don't make exactly the same classification. How different are the classification that they make? So we can examine this question by the following scenario, by asking the opposite question. Instead of asking which weight vectors solves a particular classification task, ask how do two different weight vectors perform classification of the same pattern. So we have here, we take two two temperatures and present to them the same pattern, to both of them. But the two temperatures have different weights. And the only restriction of the weights that we put on the weights is that in overall, the probability of each of the temperatures to fire for input pattern is 1/2. And we correlate between the two weights. We take the cosinus of the angle between the weight vector of temperature 1 and temperature 2 to be an adjustable parameter that we change. Okay, so we take two random weight vectors with some correlation, Q, and ask what is the probability that both of them classify any random pattern the same way. Okay, and the result is maybe a bit surprising. So this is what we did. We did a simulation, also did the calculation. So here the blue line and the simulation result are the result of the perceptron. You can do the same thing with regular perceptrons, and you see that the moment you have some correlation in the weights, the correlation in the decision, so this is the probability of equal decision, it starts from 1/2, this is just by chance, and goes to 1 when the two weight vectors are identical, and it goes from 1/2 to 1 almost linearly. If you look what happens in the temperature, you get a completely different picture. You see that in the beginning, the slope of this curve is very, very low. And the probability of the two temperatures to classify the pattern the same way increases very, very slowly, and is only significantly above chance when we are very close to 1. Okay? So you can do the calculation, and you find out that how close is it to 1/2 depends on k. As k increases, we are more and more closer to 1/2, and as k increases, the region where we are substantially more than 1/2 shrinks like 1/log k. Okay, so when k is very, very large, we have to be really, really close to 1 in order to have some correlation between the decisions of the two temperatures. And after the first time I gave this talk, Eli Nelken came to me and said that we might see this kind of behavior in the auditory cortex, primary auditory cortex of the cat. So I want to show you this example. So here we have recordings from two neurons, and on the top panel you can see the receptive fields of these neurons. So the x-axis is frequency, and the y-axis is intensity, and the color code is the intensity of the response of the neuron as to tones in this frequency and intensity, and the overall impression is that they are very similar to one another. Okay, so we can say that the synaptic weights are close and correlated. However, when you present to them the same input, this input is a bird call. This is the sound, and this is the before and after, just the background noise. And you can see that the responses of these seemingly very similar temperatures are completely different. This neuron, sorry, it's not a temperature, it's a neuron. This is the real thing.
This is the model of a temperature.
The model of a temperature. This neuron, responds mostly to the background. It doesn't even seem to have some significant response to the stimulus itself, while this neuron responds mostly to the stimulus. So you can see here identical inputs, presumably similar weights, but completely different output in the end. What I'll try to give you the intuition. What I'd like to do now is give you the intuition of why does that happen in the temperature, and why might it happen in neurons. So in order to understand that, we need to remember that the decision of the temperature is based on the maximal voltage, and the voltage, in the large n limit, is some stochastic. You can model it as some stochastic process, and some Gaussian random process with correlations, and that we have a lot of theory about from mathematics. And the extreme value theory is the theory that tells us what are the properties of the maximal of this voltage of this process in some time period. And what we get from what we know from this theory are two important things. First, that the median or the mean or the typical value of the maximal voltage is much higher than the average fluctuations. So it goes like and it increases with k, and that the standard deviation is small. So here we see the voltage trace we saw before. But now I plot the voltage in unit of one standard deviation, and you can see that even for k equals 100, which is not 2 log k is not very high, the voltage is the maximum is around three times the standard deviation of the signal, and I don't show here, but the standard deviation of the maximum is also small, and because of this large gap between the mean and the maximum, in order for the Tempotron to make the classification, because we demand of it that for the half of the pattern we want him not to fire, and for half of the pattern we want the Tempotron to fire, then the threshold, we must set the threshold of the learning, the result of the learning will be that the threshold will be much higher, will be very high compared to the fluctuation of the weight. So we have to put the threshold in the median of the distribution of the maximal voltage. And to see what the effect of this high threshold regime does, I want to look close up on this region where the voltage is maximum. So here I plot the same, the blue line is the same voltage trace, you see it crosses the threshold. And now I take the same weight, I take some new weight vectors, but correlated to the original one, and show them the same pattern again. So what you see is the red lines are just, I just did 7 realizations of different sets of weight with correlation coefficient 0.8, so really similar weights. And you see the resulting voltage potential. And what is important to note about this result is that the average of this result is the relative distance between the average of this result and the threshold and its standard deviation. So you see, if this is a Gaussian, this is a Gaussian, this is standard deviation, the probability of crossing the threshold, even though we know that the original voltage crossed the threshold, is still very low. And this phenomena becomes more and more distinct as k increases. So as k increases, this gap becomes larger and the probability is smaller. Only when will we have correlation? Only in the regime when 1 minus q is very close to 1 of the order of q is very close to 1 of the order of 1 over log k. Only then will the voltage at this time will be correlated with the voltage of the original weights. Yes.
How do we think about this with respect to your Q1? Q1 was, I thought, was sort of saying for a range of
yes.
weights.
Yes, very good. So here we don't have Q1 and Q0 because we don't have a task. We don't have a classification task. But yes, you can definitely look at Q1 as so this Q is also, so when Q1 will be the Q when we will be in this regime. So it means the result of the actually, if the result of the theory is that 1 minus Q1 is of this order of magnitude.
So it should be very small. So on your diagram, it's like Q1, Q1.
Okay. So I didn't say that the relationship is reversed. So when the size is 0, Q1 is 1, and when the size is very large, the Q1 is 0. It's the other way around. Okay, but this explains why there is no correlation. Because if there's no correlation, if there's no correlation in the decision at the time of the maximal voltage, then the overall probability of the red line to cross the threshold is again just 1/2. So 1/2 plus something small. Only when we get close, when we have order 1 probability of crossing the threshold here, that we have correlation between the decision of the two weight vectors. So, and another point, so this result brings us to some insight about the robustness of the Tempotron. On the one hand, we want to increase k as possible because the capacity increases, and on the other hand, we want as k increases, we are more sensitive to noise. So we need to find some intermediate regime. So to summarize, we saw the perceptron, the solution is simple, convex solution in space. For the temperature, we have a fragmentation, and we discussed the implications of that. The high threshold regimes results in a non-trivial connection between synaptic weights and input-output function, meaning that different weights can do the same tasks, and similar weights can do different tasks. And we talked about the robustness performance trade-off. So the last two slides will be to show you how are we extending the research, and I want to talk about the precise temperaton, what we're doing with Raoul Martin Memersheimer. And the precise temperaton is an integrated firing neuron that instead of learning to spike or not spike at all, for example, we can tell it for minus pattern don't spikes, and for plus pattern spikes at a particular time. And you want to be able to learn to teach this neuron to learn at a particular time, or in general, not just to make classification tasks, the task would be even more general task, just to generate spike patterns of the output spikes. So here we have P input patterns, and for each pattern we specify where exactly should the temperaton fire. And I will not go into the details, just we have, just to show you the results, we have an algorithm that does exactly that. So here I show you the response of the neuron to a given pattern before and after learning. So the dash is before learning, you see that it doesn't spike at all. And after learning, you see that it spikes, reaches a threshold exactly the desired output times. And we can measure the capacity of this kind of task. And we also have a theoretical result saying that the capacity decreases with K because we make the temperaton fire at specific times. It doesn't have the previous freedom it had before to choose its time. Then as you increase K, the number of restrictions increases, and this is just the line 1 over log K. And you can see it's a nice fit, even though this is an approximate theory. So to summarize, fixing the output spike patterns limits the capacity of the temperaton, but on the other hand, it's a much simpler task to learn because if you think about it, it's like a perceptron, and the solution space is again one convex volume in white space. If you have any questions.
Does your calculation have replica symmetry breaking?
Yes.
It looks like it should. So how are you dealing with that?
Well, so originally the calculation is not the regular replica symmetry calculation. So from the beginning, it's more like a first step calculation. But even that has replica symmetry breaking. That's why I showed that. That's why I'm saying I know where the solution space breaks. That's exactly the transition, and we didn't do the full replica symmetry breaking. However, in similar models like the Comity machine and parity machine, it was shown that as you increase K, the instability decreases. So in the large K limit, we hope that the results asymptotically are correct. Yes?
You have shown at the beginning how the perceptron divides the input space into two sections for classification. Do you have something similar, some insights regarding the temperature? How continuous is the division of the input space? It's harder than trying.
Well, the decision of the temperaton is also binary. It also divides the so it's so you can see from the solution space that it's not. Okay, because you have many different ways of solving the problem, these ways are not related. You can spike at the end of the pattern, and you can spike at the beginning of the patterns, and the weights that cause you to spike in the beginning and in the end are not the same weights. So if you make some linear change and take the voltage that was above the threshold at one point, put it below, you don't know what you're going to do at the rest of the time. This is exactly the point I was making in the last part of the talk. So what it means is that the max operation is very non-linear. So you don't have this linear separation of inputs. If you look at the entire patterns, you do have if you look them one by one. So each time being of length tau, it's like a perceptron pattern that is classified in some way according to whether the voltage memory potential is above or below threshold. But all in all, the patterns, it's more complicated. Yes?
So these max operations, of course, have a lot of similarities to models of complex cells, visual cortex, and you can get a lot of mileage without going all the way to max, but actually doing another softer nonlinearity, like squaring, doing energy-based methods, or raising to the fourth power. Do you think that would make your life easier in the Tempertron?
Well, the Tempertron, well, there are 2 points, I think. One that, I wrote the max, but you don't really need the max, because the Tempertron, it fires not only, the max is only an indication whether it crosses the threshold or not. So there are, the output of the Tempertron after learning is not just one spike per output. It can, it's a Poissonian rate. It can spike more than once. I think that theoretically, to analyze it, I think using the max operation is the simplest form to formulate the problem and to start to get to these equations. This is the simplest way, simplest thing to do.
You can have softmax also for Tempertron, and we've shown works quite similarly. So you can soften the max and
Or soften the threshold.
it's like softening the threshold. It is.
You still get the
like
shattering and
fixation.
everything with softmax? You still get this weird shattering with softmax and non-robustness? Or does it make things more complex?
Probably the points where shattering happens will change, but it will happen. Yeah.
Thank you.
Thank you very much.